So what we're going to do now is start doing these, drawing these MO diagrams ourselves and seeing what we can see. So we'll follow all the rules. All right, so let's do H2. Well, let's do H2 first. So what we know is that H2 has 2 electrons. Each H brings 1 electron. So I'm going to put it here and put it here. I'm mixing up my arrows, not my best work. Okay, the 1s's come together to form a sigma bonding MO and a sigma antibonding MO. We put our electrons. How many total electrons do we have in H2? We said 2. So we start from the bottom, we put them in. 1, 2. All right, so what this is saying, we have 2 electrons in a sigma bonding MO. This should be holding those H atoms together, right? Predicting a bond between there. Another way to sort of test how stable a bond is to use bond order. And the formula for this is, it's 1/2 times the number of bonding electrons minus the antibonding electrons, or bonding minus antibonding divided by 2. So if we do this, bonding electrons are 2 in H2 minus 0, antibonding over 2. So that equals 1. The bond order for this molecule, H2, would be 1. And what we know is that corresponds to a single bond, right? A bond order of 1 is a single bond. Bond order of 2 corresponds to something like a double bond. 3 would be a triple bond. And then remember we saw resonance and things, you could see fun things like 1 1/3 bond orders and things like that. So let's do H2. All right, H2 plus. Now this is the cation of H2. So how many total electrons do I have? H by itself has 1. 2 H's have 2, but then 2H with a plus means I have to take 1 away. So I only have 1 electron available. Now do I put it on this side or this side? It really doesn't matter. And this is where I would say we don't really care about putting electrons in here. We know they're there. I want to use these 1s atomic orbitals to figure out that I'm making a sigma and a sigma star. That's important to me. But I don't really care who gets the electron. So you can draw it over here or over here, right? Or don't even worry about it. Most important now with the MO is to put it into the MO diagram. So we start from the lowest energy MO, and I have 1 electron. So I put him in there. And that's it. This is the important part. So now I can calculate the bond order. So bonding electrons minus antibonding electrons divided by 2. Bonding electrons minus no antibonding divided by 2 equals 1/2, a bond order of 1/2. So what this means is there's bonding character, right? But it's not as strong as a single bond. It's a little bit weaker. Okay? We can see this with helium. So let's try dihelium and the helium cation. All right, so we already have our MOs. We know we're only starting with a 1s atomic orbital from each, so the MO diagram won't change, just as the number of electrons. So how many total electrons in dihelium? Each helium atom brings 2 electrons. So helium has 2. 2 heliums then should have 4. Okay, so I expect to see 4 electrons. So I start from the lowest to the highest. All right, this is filled up. Nice work. Let's check the bond order. Bonding minus antibonding divided by 2 equals 2 minus 2 is 0 divided by 0. So the bond order for He2 is 0. This predicts then that there's no electron density between these guys. So MO theory predicts that dihelium doesn't exist. There's no stable bond holding them together. Let's check the helium cation. So in this case we have 3 electrons. 1, 2, 3. Now we can calculate our bond order. So it's 2 bonding minus 1 antibonding divided by 2 equals 1/2, bond order of 1/2. So MO theory predicts that you might be able to find some dihelium cation out there, right? There is some bonding character holding them together.